Linear approximation, section 4.2. Sometimes it's useful to approximate a function at a point a f of a by a straight line to get a linear approximation. This essentially is a point-slope form, but L of x linear approximation is equal to f of a plus f prime of a, the slope, times the quantity x minus a. Anyway, we can use linear approximation to approximate x squared minus 4x plus 4 with a straight line when x is 3. So this first step, compute the derivative. So that's going to be derivative x squared minus 4. Use the power rule. It'll be 2x minus 4. And then the slope is when x is 3. Not the slope when x is 3, so that'd be f prime of 3. So that's 2 times 3 minus 4, which would be equal to 2. And then we also want to compute f of 3 with the original formula. That'll be 3 squared minus 4 times 3 plus 4. And that's going to be equal to 1. Okay. Okay, so then we can plug in L of x is equal to f of 3, which is 1, plus the slope, which is 2, times the quantity x minus 3. And then if we simplify that, we can get distribute the 2, we'll get 2x minus 6 plus 1 is minus 5. So L of x is 2x minus 5. Okay, so I think a picture kind of helps your intuition, so I'm going to make a picture here. Another piece of paper. So the original function is a parabola. Okay, so we can plug in some points and sketch the graph, I guess. But this is this function here. Actually, we can factor this. This is x minus 2 quantity squared is x minus 2 times x minus 2. So it's going to be a parabola with the vertex opening up. The vertex is going to be at when x is 2. Or we can just plot some points to plug in numbers, but it's a parabola opening up with vertex at 2. If we put in a 0 here, f of 0 is going to 0 plus minus 0 is 4. So f of 0 is 4, and f of 4 is going to be also equal to 4. And connect the dot. F of these should be at 1. So this is a parabola, and then we have we're going to approximate with a straight line. L of x is equal to 2x minus 5. So the y-intercept there is at 5. Okay, so so the y-intercept at 5, and it's going to be tangent at 3. So it's going to be the line is going to be something like this. So this is our tangent line. So at 3. So so when x is close to 3, the line is actually pretty close to the parabola. As x gets further from 3, then the line is not so close. So anyway, this is this is L of x here, and this is our original function f of x in red here, and the linear approximation is pretty accurate as long as we don't stray too far from the tangent point, the point of tangency. Okay, so just to give another example, perhaps a more useful example, we want to estimate square root of 3 using linear approximation. So we'll let f of x equal square root of x and take the derivative. You can write this as x to the half power and use the power rule to take the derivative. This will be 1/2 x to the minus 1/2 power, was 1 over 2 square root of x. The negative exponent is the same as the positive exponent in the denominator. So then we compute the slope. So we want a perfect square that's close to 3. So 2 squared is 4. That's pretty close to 3. We'll compute f prime of 4. That's going to be 1 over 2 square root of 4. Square root of 4 is 2. 2 times 2 is 4. So the slope when x is 4 is going to be 1/4. And we want to compute f of 4. F of 4 is just the square root of 4, which is 2. So L of x is going to be f of 4 plus f prime of 4 times the quantity x minus 4. So that's going to be f of 4 is 2. Square root of 4 is 2. F prime of 4 is 1/4. X minus 4. And we could leave it like that, or if you want, you could distribute the 1/4. You could write this as 1/4 x. 1/4 times negative 4 is negative 1, so negative 1 plus 2 is 1. So it's 1/4 x plus 1. Okay, so L of 3 is going to be 1/4 times 3 plus 1, which is 1 3/4, or as a decimal is 1.75. There is a procedure that's kind of like long division for computing square roots. There's various ways of finding square roots, but so this is our estimate using a straight line approximation. But let's compare it to the actual square root of 3, and see if I remember how to do this. They used to teach this. I went to school before there were calculators, so they used to teach it. I learned it in 8th grade. A procedure for getting the square roots of numbers that is a little bit like long division. So we want the square root of 3, so we're going to write 3 here and put a 0 in front. And we want to add some zeros, but we're going to pair these up. We start with a perfect square that is less than 3. 1 squared is less than 3, and we want to put that on top. And 1 squared is 1, and you get remainder 2. And we want to bring down 2 zeros. And what we want to do is double the number on top. So 2 times 1 is 2. And then we add an extra spot here. And we want 20-something divided into 200. And so I'm going to estimate 7. Whatever goes on top has to go here. And then you multiply. So 7 times 7 is 49. Carry the 4. 7 times 2 is 14. And 4 is 18. And then you have remainder 11. Bring down 2 zeros. We double the number on top again. So it's twice 17 is 34. And then we have an extra digit. So it's 340 something goes into 1100. I'll estimate 3 times. So 3 goes on top and 3 goes down here. 3 times 3 is 9. 3 times 4 is 12. Carry the 1. 3 times 3 is 9 and 1 is 10. And you get remainder 71. Bring down 2 more zeros. Double the number on top. That'll be 346. Add an extra digit. So 3,460 something into 7,100. We'll estimate 2 times. So I'll put a 2 on top, a 2 down here. 2 times 2 is 4. 2 times 6 is 12. Carry the 1. 2 times 4 is 8, and 1 is 9. 2 times 3 is 6. And you get remainder, let's see, is 6, 7, 176. Okay, so so this is reasonably close. With linear approximation, we got 1.75. This is 1.73 using an exact methods. So that's reasonably close. Okay, so let's actually make a picture here of this one also, because I think the picture helps your intuition. So our function f of x is square root of x. Okay, so square root of 4 is 2, and that's actually our point of tangency here. Square root of 1 is 1, square root of 0 is 0. So the curve, it's a semi-parabola. It's a piece of a parabola, and that's f of x. And our tangent line is L of x equal 1/4 x plus 1. So L of x, the y-intercept is 1, and the slope is 1/4. So if you go over 4, you go up 1. So it'll actually go through the point of tangency here. So this is L of x here, and the original function is in red. That's f of x, and you can see that if x is close to 4, then L of x is going to be pretty close to f of x. So that's sort of the graphical sort of idea. Okay, so there's also another way of doing linear approximation, and that's with differentials. You remember the definition of derivative using Leibniz notation. I seem to have lost my camera here. In Leibniz notation, the derivative is a limit as delta x goes to 0 of delta y over delta x. So this is the change of y over the change of x. Basically, the slope of the secant line, this is the slope of the tangent line, equals at the limit, a limiting function of the slope of the secant line. Up to this point in time, we regard we didn't separate the dy and the dx. We regard that as a fixed quantity. It's a limit of a ratio, but it's the dy dx itself. We didn't regard that as a ratio, but as a limit of ratios. But we can actually define dy and dx separately, and there's a this picture may sort of help, so that if we think of delta y as the difference between f of x and f of a. So delta y is the difference between f of x and f of a, and dy is the difference between between L of x and L of a. So that's that difference there. And delta x or dx are both going to be the same. They're going to be a difference between a and x. So then a dy is going to be an approximation for, or delta y is going to be an approximation for dy. So anyway, we can, if we look at this equation for L of x minus f of a, we're calling that dy. is equal to f prime of a, and then x minus a, we can call that dx. So we have dy is equal to f prime of ia times dx. So dy and dx are called differentials, and so we can use those. Here's an example. The radius of the Earth was measured to be 4,000 miles plus or minus 100 miles. What is the possible error in the volume? So we can use the formula V equals 4/3 pi r cubed, and then take the derivative. That means, so the derivative is dy dx. Our dy dr is going to be, if we take the derivative with respect to r, dv dr rather, dv dr is just going to be 4/3 times 3 times pi r squared. The 3's will cancel, so this is 4 pi r squared. And then if we separate the dv and the r, so multiply both sides by dr, and we get dv is equal to 4 pi r squared dr. And then we can take, estimate pi to be about approximately 3.14. The radius of the Earth is 4,000 miles, and the differential is a plus or minus 100, so that's going to be the dr, and if you multiply that out, it's 20 billion 96, a little over 20 billion cubic miles. So the possible error in the volume, a small error in the radius, makes a potentially very large error in the volume. So anyway, that's an application of differentials. We could have used a previous example. Previously we used linear approximation to estimate the square root of 3. We could have used differentials there also. So when we took the derivative of y with respect to x, we got dy dx is 1 over 2 root 2. That was, we did that before, 1 over 2 root x rather. We had done that previously. And then again, we want to separate the dy and dx. So we can write this dy is equal to 1 over 2 root x dx. And then since 4 is a perfect square that is close to 3, we can let x equal 4. And then because 3 is 1 less than 4, we could take dx to be negative 1. So so if we plug it in this formula for dy, if we replace dx with negative 1 and x with 4, we get a dy is equal to negative 1/4. So if we do, so that means the square root of 3 is approximately square root of 4 minus 1/4, which is about 1.75, which was what we had before. So so anyway, we could have used differentials there. And that concludes this presentation.